Okay, so welcome back to a late lecture, but yeah, today was a busy day. So, okay, let's see. So we were doing this lemma, no, this theorem, right? So simultaneous diagonalization. I don't, what happened? Somebody again. So what we know is we have a, so last time what we talked about was that big theorem that we proved that linear transformation on the finite dimensional vector space, blah, 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 is diagonalizable if and only if its minimal polynomial has simple roots, meaning it has no repeated roots. Right? And then after that, we sort of stopped. We have moved on to this particular thing. And I think we had a lemma somewhere, right? Yeah. So before we are going to use that lemma, that's why I'm sort of saying it. So we had a lemma. So, okay, we want to prove this theorem. Suppose V is a finite dimensional vector space. Ti are linear transformations from V to V, and all of them are diagonalizable. So each of them individually has a basis of eigenvectors with respect to which it's a diagonal matrix. The claim is if Ti and Tj commute for every I and j, then you can choose a common basis with respect to which all of them are diagonalizable or are diagonal. Okay. And before that, there was a thing that I had claimed. Is this it? Yeah. Right. So this was the end of a proof, so I should probably say that. So there was a previous lemma that I had claimed, which was that if you have a t-stable, suppose T is a linear transformation, and on V to V, and W is a t-stable subspace. So T sends all of W to W itself. Then the characteristic and minimal polynomials for W divide the characteristic and minimal polynomials for V. Okay, the reason why I proved that lemma is that it will be useful in the proof of this theorem. So let us now start with the proof of the theorem. Maybe I may as well start on that side, I guess. Okay, so let's start. So how many I start? Proof. So okay, so first case is suppose all the TIs are lambda I times n. So say, so maybe I should do it in cases. So let's okay, so okay, fine. Say I'll just put a bullet point here. All sorry, so say Ti equals lambda I times identity. Okay, so suppose I have this very nice situation, the nicest possible situation, that all of these are scalar maps. Then you are done, right? Then you are done because then you have any basis of V with respect to that, all of them are diagonal because they're already diagonal. We want to say there exists a basis. Well, I'll just say any basis of V works. Okay. The second case is if n equals 1. What happens when n equals 1? When n equals 1, you have a 1 by 1 matrix. You have a linear map from the field to itself. That's just literally multiplying by a scalar, right? Linear maps are the same as matrices. 1 by 1 matrices are scalars. So when n equals 1, you have a scalar, and a scalar is, of course, a scalar times the identity for 1 by 1. So in particular, n equals 1 is proved. The n equals 1 case follows. Okay, so n equals 1 is done, and the case when PI are all scalar multiples of the all scalar maps, basically. All PI are scalar maps. Okay, so now we will assume that n is bigger than 1, of course. But we will also say, we'll also look at the case that at least one of the PIs is not a scalar. What does that mean? Well, these are precisely the maps where all the eigenvalues are equal. Remember, they are diagonal maps or diagonalizable maps. But they are precisely the diagonal maps where all the eigenvalues are equal. So if a PI, which is diagonalizable, is not a scalar map, then it must have at least two distinct eigenvalues. And of course, that means n is bigger equals 2. Okay, so now henceforth, suppose this thing, we will prove it, of course, by induction on n, and n equals 1 is directly done because of this. So now we prove. Now we show the result. by induction on n bigger equals 1. Okay, and the base case is done above. The base case was just done because, yeah. And in the remaining case, in the induction step, we will say that let's look at some induction step. Okay, so again, we can assume by the previous point from above, we may assume. We may assume, or we can assume, there exists an I in I such that Ti has at least two distinct eigenvalues. Should I say I or should I say I naught? I want to say I naught. Just to distinguish it from the other I. So Ti naught has two distinct eigenvalues. So it has bigger equals to right? If it had only one eigenvalue, then it would be lambda times identity. Because these are all diagonalizing. Okay. So okay, which is the same as this is the same as saying Ti naught is not in the span of the identity. Sorry, this is the identity matrix. I meant the identity linear transformation. Okay, so that is the right. So that's what we can assume. Okay, now what I'm going to do is we will look at the eigenspaces themselves, right? So now the claim is, so let's say. So that means, so first of all, if it has at least two distinct eigenvalues, did I say the dimension of V was n? I did not. Okay, so let's say let n equals dimension of V. Okay, and say Ti naught has eigenvalues lambda j, so I will call it j, so that distinguishes from I, lambda j with geometric multiplicity with dimension v lambda j. Let's give this a name, let's say mj. And what do we know? Since there are at least two, each of these is a positive number and there are at least two of them. Therefore, each of these is strictly less than n. Right? So therefore, I must say that, yeah, so it is. So yeah, you assume the dimension of n, and mj belongs to open 0, comma n. Right? It cannot be 0 and it cannot be full because in every other mj would be 0, and there are at least two which are not 0. Okay, great. Okay, so now we will look at one of these, right? So okay, maybe I should first say each of these is stable. So claim I'll do that. This was the theorem. Yes, today at least, yeah, today, okay, this is finished very quickly, and then I will start the Jordan canonical form. Okay, so here, each lambda is Ti stable. So what is V lambda j? V lambda j is the eigenspace for Ti naught. I am saying take every other I as well, including Ti naught. Of course, Ti naught preserves V lambda j because it just rescales by lambda j. But every Ti also preserves that. That is the claim. Okay, so proof. The proof is not bad. The proof is very simple actually. Let's take, so if V belongs to V lambda j and I in I, we just calculate. So what do we want to show? We want to show that we want to show that Ti times V should be in V lambda j. What is the definition of V lambda j? It is precisely the lambda j ideal space of this map. So let's apply this map and check that you get the correct rescaling. So Ti naught applied to this. What is this? This is Ti naught composed with Ti applied to V. But now you know that the Ti is commute. So this is Ti composed Ti naught applied to V. But what is this? Is the same as Ti naught of V, and Ti naught of V is exactly lambda j. I'm skipping a step here, but fine. You just say that this becomes Ti naught of V. But then that's great. So you have some vector here such that Ti naught acts on it and produces lambda j, which means that Ti of V must be in is in the lambda j eigenspace for Ti naught. Great. So that is what it is. Okay. Now here is the point. What do I want to do? I want to say. So what I want to say is that every V lambda j, which is a smaller dimension, and now you see it is Ti stable. That means that I can replace V itself by V lambda j of a smaller dimension, for which I know, and every Ti acts from V lambda j to V lambda j. So the theorem applies for a smaller dimensional subspace. I can use the induction hypothesis and I'm done. By the induction hypothesis, every V lambda j, Ti has a basis which is simultaneously an eigenbasis for all the Ti. Take the union of those bases, that is the union, that's the basis of the coproduct, right? Take the disjoint union or coproduct of those bases, that is the basis of the coproduct of the V lambda j's, and that is exactly all of V. So we are done. There's a small gap. What is the small gap? Think about it. Okay, if you found the gap, then excellent. And if you just want to enjoy the show, for those of you who want to enjoy the show, forget, I haven't seen any. Fine. So what's the point? The point is you have to verify that all the assumptions held. And there was one extra assumption there, which we have not yet verified, which is that every single Ti, not only they commute, and not only do they preserve V lambda j to V lambda j, but they are also diagonalizable. And we have not verified. How do you know that each Ti or Ti naught? Ti naught is diagonalizable. It acts by a scalar. How do you know that the Ti's are diagonalizable on V lambda j? We don't know that. So we must verify that. And to verify that, we use this theorem that I have took so long to prove using the lemmas and the interpolation polynomials last time. So that's why it all builds up. So now we are going to use that theorem to prove that this happens. Okay? Basically, the theorem that says that the minimal polynomial has to have simple roots. Okay, so let's do this. So, and we will use the lemma that we did last time, which is that the minimal polynomial for V lambda j for each Ti must divide the minimal polynomial for all of V for the Ti, because these are T stable. So the whole point is this Ti stable will allow us to use the lemma and the theorem both from last class to claim that it's diagonalizable, and therefore we can use the induction hypothesis to get eigenbasis. So this is a really, this is really now finally we are in the last month basically of the course, because I think we are past the 22nd and I think your classes end on the 22nd of November or something. So it's time to start using everything and sort of combine all the instruments into some big symphony. So that's what we are doing. We are combining all these ingredients together and coming up with the proof. Okay, so first of all the claim is proved. Great. But now as I said, we can't apply the induction hypothesis. So the idea, the goal or idea would be to apply the induction hypothesis to each Vj, to apply the induction hypothesis to each V lambda j, because the dimension is between 0 and n. Strictly, so the dimension is less than n. Therefore, each V lambda j has an eigenbasis, simultaneous eigenbasis. for all ti. Right? And since these are eigenspaces with different eigenvalues for a single linear transformation, their sum is the direct sum, and the sum is equal to all of V because this is diagonalizable. So this would imply there exists a simultaneous eigenbasis for the direct sum over V lambda j, but that is exactly equal to V, and this is because Ti naught, with respect to which you are taking the eigenspace, is diagonalizable. That is the, I mean, that's not the idea, that is exactly the proof. But to apply the induction hypothesis, you need to prove that each Ti is diagonalizable on the subspace where it is stable. Okay, so for this it remains to prove, to apply the induction hypothesis, it remains to prove that each Ti is diagonalizable on each V lambda j. But to apply the induction hypothesis, we need to show that this is true. So why is this true? Okay, so that is point number one. So to show this will hold. Maybe I should say it the other way. So by the theorem from last class, we need to show this. Equivalently, we need to show that the minimal polynomial of Ti on V lambda j has no repeated roots. Okay? We need to show P min Ti at V lambda j of x has no repeated roots. That was because the theorem said that if you have any linear transformation acting on a vector space whose minimal polynomial has no repeated roots, then that transformation on that vector space is diagonalizable. And that's exactly what we want. So that's what we need to prove. And now finally, by the lemma from last class. So how do you prove this? So we need to show this now. How do you show that some minimal polynomial has no repeated roots? So now you play the following trick. So by the lemma from last. So okay, but now I should say, but note that I'll just say, but note that. No, what do we know? We know that Ti is diagonalizable on V. Okay. Therefore, by the theorem, by the same theorem from last class, the minimal polynomial of Ti when restricted to all of V has no repeated roots. And also, polynomial actually factorizes into a product of linear factors and is a product of linear factors. So it's like x minus lambda 1, x minus lambda 2, x minus lambda k, and all the lambda i's are distinct. There are no repeated roots. Linear factors. So I could just have summarized both of them by saying is a product of distinct linear factors, but fine. X minus lambda. Okay, so it's a product of such factors, and all the factors are distinct. So I know that Ti is diagonalizable on V. Therefore, the full space polynomial has this property. What can you say about the minimal polynomial on a subspace of V? That is where I use the lemma. So finally, by the lemma from last time, that polynomial, the one here, divides this polynomial here. But this is a product of repeated, non-repeating factors. This is therefore a product of a subset of those. But of course, a subset of non-repeating factors cannot repeat. So you're done. And now by the lemma from last class, this second, let's give this a name. Let's give both of them names. Let's call this Q j of x for j for lambda j. And let's call this is equal to, this is Q of x. So I know that Q of x has no repeated factors and is a product of linear factors. Qj of x must divide Q of x, so it has the same property. Divides Q of x. Hence also has no repeated roots. And therefore I'm done. Right? The minimal polynomial of Ti on each v lambda j has no repeated roots. Therefore, each Ti is indeed diagonal and breaks up into a product of linear factors. So I'll just say has the same properties. Has the same properties. These two properties. Therefore, this polynomial has no repeated roots and is a product of linear factors. Therefore, by the theorem, indeed, well, that's what we wanted to prove. Therefore, by the theorem from last class, backtracking, this Ti is diagonalizable on the lambda j, and therefore, backtracking again, we can apply the induction hypothesis because we now know this. And once you apply the induction hypothesis to each eigenspace with respect to just one Ti naught, to each eigenspace, you can check that indeed, yes, each of these is a simultaneous eigenbasis, simultaneous for all the Ti's, and therefore, when you take a direct sum, take the union of those bases and you are done. Okay, so that's that. I think that is the end of simultaneous diagonalizability. Yes. And now we come to the main thing, the one big result. So this itself will take up today's class and a bunch of next week's class. So there's no sort of easy way about proving this. So finally, this is the existence of the Jordan canonical form. Okay, and there's no easy way of proving this, but I managed to cook up some sources. Eventually, I think the proof I'm taking is from a website from Princeton University's math department. Somebody wrote up a proof, which was self-contained. And so I found that, and that's what I'm doing. Okay, let's go to Jordan canonical form. Okay. Yeah. Okay, so let me go back to this thing about eigenvectors. We talked about the point of a diagonal matrix or a diagonalizable matrix was that you can understand how powers of this matrix act on the general vector. Right? So let me just remind you, recall. So if you have, let's say, A equals B equals lambda 1, lambda 2, lambda n, diagonal matrix, then you know how it acts, powers of this act on a vector. If A equals this thing, then A to the k summation, or let's say B to the k, let's say. I goes from 1 to n, summation Ci, Ei is what? It is literally, you know what it is. Summation I goes from 1 to n, Ci, lambda I to the k Ei. And that's obvious. And so we have seen this, I mean, we discussed this plenty of times. And then similarly, if you have A equals PDP inverse, right? Then again, you can talk about A to the k acting on summation Ci, PEI. This is a new basis because P is invertible. And this is again, once again, summation Ci, lambda I to the k, PEI. I goes from 1 to n. Okay. Right? So that's what you can do. Now I'm going to take a different matrix where I will just do very simple. I'll take the same lambda, not different lambda. I'll take lambda, 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 and I'll put a 1 on the diagonal above it. So it's called a super diagonal. Yeah, like the sub-diagonal and super diagonal. So I will put a lambda on a row of lambdas in the main diagonal and 1s on the super diagonal. And such a matrix, a very special form, is called a Jordan block. So instead, if instead now say equals, now say, I'll do a 3 by 3 example. Lambda, 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 1, 1, 0, 0, 0, 0. Okay? Then actually, well, you can calculate, you can check by induction that A to the k, of course, it's triangular, so lambda to the k, lambda to the k, lambda to the k. This is k, lambda to the k minus 1. This also. And this is k choose 2, lambda to the k minus 2. Okay? This is in your exercises as well, I think. So you don't need to see this if you don't want to. And anyway, the point is, therefore, you can predict, so we can also, once again, we can tell people, like we can calculate exactly how this happens. Once again, compute, explicitly compute. Either both of these expressions, one of them is of course A to the k times summation Ci Ei. But also we can compute P, A, P. Let me call this something else. Let me call this J lambda, okay? I'll say J lambda to the k and J lambda times summation Ci PEI. Okay, so you can again calculate both of these expressions. This is misleading. Which means if you can do this, by the way, when n equals 1, when it's not 3 by 3 but 1 by 1, then 1 by 1 is the same as a diagonal matrix. So there is some overlap between these two notions. The point is, if you can do this, then you can then actually calculate something like this. Sorry, to the k. You can calculate something like this for every block diagonal matrix each of whose diagonal blocks looks like this or like that. Oh, what happened? Just a cap fell off. You can do that, right? And therefore you can calculate for conjugates as well. Now the remarkable thing is, at least when, say, suppose your field is complex numbers or the field is algebraically closed, then these stand for every single matrix, not just most matrices, some kind of special matrices, no, every single matrix can be written in this way, or as a block diagonal matrix, each of whose diagonal blocks is like this. So therefore, in principle, we can actually calculate the action of powers of any matrix on any vector. So that's the goal of Jordan-canonical. That's one of the ways you can motivate Jordan-canonical. So more generally now, so now let me just say that. So more generally, let's say putting such matrices together. We understand a to the k and p, or let's say m to the k matrices, and p m to the k p inverse, which is the same as saying p m p inverse to the k for m of the form. Actually, I should give this a different name. This is 3 by 3, so I'll call this j lambda 3, j 3 comma lambda actually. Okay, so I'll say that here. So j m1 lambda 1, j m2 lambda 2, dot 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 j m k maybe m r I r. Okay. Everything else is. So more generally, we understand those. And as I said, the main theorem that we will prove next time probably, or we'll finish the proof of it next time, is that every single matrix looks like this, up to conjugation, and over an algebraically closed field. Remarkably, if you have any matrix which is square and all its eigenvalues are in the field, so for example, this happens if your field is the complex numbers, then A is conjugate to something like this. To something like, to some m meaning this m, to some matrix m of this form. So every matrix, all of whose eigenvalues lie in the field, is conjugate exactly to such a matrix. So that's why basically what we are saying is, no, we don't just understand diagonal maps and diagonalizable maps and how they act on vectors. If you can understand, if say your field is algebraically closed, all the eigenvalues are in the field, then take any matrix. It doesn't matter which matrix you take. It will be conjugate to something like this, and therefore you can understand the powers and even polynomial, linear combinations of polynomials in such a matrix, acting on the general vector in the field, in the vector space. That's the point of the Jordan canonical form. So these guys, each of these guys is called a Jordan block, and such a matrix is said to be in Jordan canonical form. Let us now define. So for example, over the complex numbers, we understand A times V for all matrices A in the complex n cross n, and vectors which are of course Ci, Pei. So you write down A in terms of something like this, P inverse, and then Ci, P. Or I can even say A to the K times B. I goes from 1 to n. Where A equals P times M times P inverse. That P. Okay. So that's what the thing is. Definitions. Now let us write down the definition of Jordan canonical form, a Jordan block. A Jordan block is a square matrix is a matrix J. I didn't say anything. Let's say M comma lambda, which is you put lambdas on the diagonal, make the matrix upper triangular. You put ones here. One is an element in any field, so I can do that, and you put zeros everywhere. Okay. And a matrix is Jordan canonical form. If it's a block diagonal matrix, every block is a Jordan block. A belongs to F to the n cross n, is in JCF, which I will expand as Jordan canonical form. If A is block diagonal, let's say I'll call it M1, M2, MK, with each Mi a Jordan block. That's a Jordan canonical form matrix. So that's the definition, and now I guess I can probably just But now, okay, if you look at this matrix, right, it's upper triangular. So what are all its eigenvalues? These are exactly the diagonal entries, which are all lambdas. Okay, so clearly that means the algebraic multiplicity of a Jordan block for lambda is n, everyone. What about the geometric multiplicity? And you can check, and that is the homework problem because of which I had to update your homework today morning. Which says that the geometric multiplicity of any Jordan block is always 1. So unless it's 1 by 1, such a matrix cannot be diagonalizable because the AM, you get the AM-GM inequality, not equality. Okay, so homework. The geometric multiplicity of lambda of the Jordan block J and lambda equals 1. This is for all fields F, lambda scalars in F, and M will equals 1. The geometric multiplicity of lambda of this matrix is 1 for all fields, scalars, and sizes. I'm supposed to put it here. Oh, okay. That's why I didn't want to. I should not have put this because I'm saying a K here. This should be maybe an R here. This is the k. I can't leave the same k here. Here I can probably say r as well. Why not? Okay, fine. Okay, so this is done. Now let us write down the main theorem. Yeah, so beyond the homework, now I think I can. Yeah, right. Get the main theorem. Then we will see an example, some properties, and we start to prove the theorem. Okay, yeah. Okay, great. So this is done. Yeah, so here we go. Theorem, the theorem of the Jordan canonical form. Let's just better pen. So okay, suppose I have, let's say D is finite dimensional. Okay, T is a linear map. T is a linear map, which and such that the characteristic polynomial splits as a product of linear factors over the field itself. Pt of x splits as a product of linear factors over x. Okay, I think this was all the assumptions. Yeah, then there exists, it's very simple, then there exists an ordered basis with respect to which the matrix, the coordinate matrix of T is in Jordan canonical form. Ordered basis such that the matrix, the coordinate matrix of T with respect to B comma B is in Jordan canonical form. That is the theorem. Basically, it says the moment your field is algebraically closed, or at least your matrix characteristic polynomial factors in that field, it is in Jordan canonical form. Sorry, basically the transformation is in Jordan canonical form with respect to at least one vector, one basis. Okay. So now, I won't prove this just yet. We have, yeah, I'll start the proof today. Yeah, there are a bunch of lemmas, and so I want to start the proof today. 1, 2, and 3. We better start the proof today. And do all of this, and then let's see. 4, 5, 6, 7. I don't know how I'm going to get there next class. We'll figure out what to do. Okay, I need to finish that much. Okay, fine. I know that I have to finish today. It might take a little longer than usual, but sorry, bear with me, please. Okay, so let's see. So first of all, now let me show you an example, a very, very well-known example, although you don't know it as a Jordan canonical form example, of a linear transformation on a finite dimensional vector space, which has a very, very natural but slightly well-used basis with where it's in Jordan canonical form. Let n bigger equals 1. Sorry, first of all, the field is the real numbers. And now let me define first of all for you the vector space. And Vn is a subspace of the space of polynomials. B of degree at most n minus 1. So V1 is the space of constants V2 is the space of linear and constants and so on. Okay? And now the point is this has degree n. The dimension of Dn, sorry, not degree, the dimension of Dn. And now I've told you the vector space, the field, I need to tell you the T. The T is the differentiation now. That T of F, so F is an element of the vector space, is d dx of F, which is F prime, and I'm going to call it as del F. So del is like the derivative with respect to x. Okay. And now I'm saying there exists an ordered basis. Well, you might suspect which basis can it be? It has to be the monomial basis. But that's not quite true because we want lambdas here and we want ones here. And the ones here is the problem. The lambdas, by the way, are going to be 0 because lambda is like saying look at the same degree. You know, if you take the monomials, then when you write down x cubed and take the derivative, you would get something times x cubed, lambda times x cubed plus 1 times x squared. And so already both are wrong. The lambda is not wrong, the lambda must be 0, but the 1 is wrong. Okay? So that's why you have to tweak the basis a little bit. And so the basis that you're going to use is not the monomial basis. Then the ordered basis B in the theorem is not the monomial basis, or standard basis. What basis? That is the basis 1 x squared x to the n minus 1. It is not that. But is what I will call at least the Taylor basis. What is the Taylor basis? It is the basis of Taylor polynomials. It's the basis, it's the kind of monomials you see when you calculate Taylor series and Taylor polynomials. So in that you have to divide by stuff. So basically you take 1 x divided by 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, and so on. Okay. This is B. 1, which is 1 over 0, x to the 0 over 0 factorial, x to the 1 over 1 factorial, x squared over 2 factorial, x to the n minus 1 over n minus 1 factorial. This is the monomial. Now, with respect to this, if you differentiate something like this, am I doing it this way or the other way? You can check. I hope it is this one. If not, it is the reverse one. Note that. I hope this is true, but you can check. Note that the matrix of differentiation with respect to this basis is precisely the matrix with zeros on the diagonal, zeros below the diagonal, ones just above and 0. And this is literally J, the Jordan block of n, 0. Okay, so that's an example of a Jordan canonical form. The differentiation operator is indeed in Jordan canonical form with respect to the Taylor basis. Okay, so now let's write down some consequences of this. Should I write them down on one board? Why not? Let's write on that board. So the theorem here is very simple, right? It just says that the moment your eigenvalues lie in the field, so for example, if you are a complex, the field is complex numbers, then indeed every polynomial splits, so all eigenvalues of all matrices are in C. But basically, the moment you have that, there exists an ordered basis of V, such that the coordinate matrix of the transformation is in Jordan canonical form. Okay, so let's see. So the corollary okay, let's see. I need to write some things down. This thing, fine. Suppose A equals exactly the kind of matrix we had written down. Let me just say this is, let's call this not B but M because I was calling it M. Yeah. Okay, so now let's calculate for such a Jordan block everything. It's characteristic polynomial, it's AM, it's GM, and so on. Okay, so corollary, say A equals P M P inverse, like we had said earlier, and M is exactly J M1 lambda 1, J M R lambda R. It's a block diagonal matrix with Jordan blocks as the diagonal blocks. Okay, and of course, therefore, this is in JC is in Jordan canonical form because that's the definition. Then, okay, let's see. So, what all do we know? First of all, these lambda i's are all of the eigenvalues of A. That is basically clear because these A, I mean, the eigenvalues of A are the eigenvalues of M. M is a triangular matrix, so of course the diagonal matrices are the eigenvalues. So this is clear. Lambda 1, lambda R are all of the eigenvalues of A. Anything else in part 1? Well, let's say that each lambda I occurring, of course, n by m times. Now notice, I'm not saying that the lambdas are distinct. So if lambda 1 and lambda 2 are the same number, they will occur m1 plus m2 times. And you're saying each lambda I occurs m I times. You can group together equal eigenvalues. Or rather, more precisely, the algebraic multiplicity of each lambda I is in this way that I'm writing it of lambda I. Sorry. Or for any lambda basically, is the summation over all the I such that lambda I equals lambda of mi. Right? The mi is the dimension of that, so yeah, number of times that root occurs. And what about the geometric multiplicity? Is that part 2? No. Because of the homework problem that I told you, the geometric multiplicity of a block diagonal matrix of particular eigenvalue is the geometric multiplicity in each of the blocks. So of course you have to only, for the lambda's geometric multiplicity, you only have to look at the Jordan blocks whose diagonals are lambda. Right? So whenever lambda equals lambda. And for each of those, I just gave you a homework problem today, in today's lecture, which said that the geometric multiplicity for every single block is 1. So you just literally have to count the number of ones, which is the number of blocks where this happens. And instead of mi, you write 1. So it's just the number of blocks where lambda I equals lambda. That's all. The number of blocks, not the sum total of sizes of those blocks. And gm of lambda. And instead of saying number of blocks, I'll just say it this way: lambda I equals lambda 1. That is part 1 of the corollary. And that's again, as I said, obvious from how Jordan canonical forms work, right? So this is just number of Jordan blocks. Number of Jordan blocks. Okay. Part 2 is that A is diagonalizable if and only if obviously M is diagonalizable. And now look, AM equals GM if and only if M equals GM. But that means every MI is 1. MI is 1 is these are 1 by 1 Jordan. Every Jordan block is 1 cross 1. So they are just diagonal matrices. It's a matrix of usual scalars on the main diagonal, i.e. a diagonal matrix. So A is diagonalizable if and only if M is diagonalizable. If and only if each MI is 1. for all I. Mi, Mj, Mi. Part 3. Okay, so first of all, basically here we calculate characteristic and minimal polynomials. Pa of x is Pm of x, and that turns out to be a product of the. Well, this is a triangular matrix, so it's a product first of all of we're going to say J. I'm going to say I equals 1 to R. Of that. So it's this determinant of some triangular matrix thing, so we know what it is. It's x minus lambda I to the m. And I think we already said that minimal polynomials and characteristic polynomials are both, of course, invariant, unchanged under conjugation. Yeah. So, and P min comma A of x equals P min comma M of x. Now, what is the P min? What is the minimal polynomial? Well, you see, you can check. Oh my God. Okay, I need to tell this in the homework. Jeez. I should update that. I'll try to remember to update the homework. The point is, we can calculate the minimal polynomial of a Jordan block. We will do that. Maybe I should not do that. Okay, but you can check this. P min of x equals yeah. So basically, you have to look at the Jordan blocks and what are their characteristic or minimal polynomials. Turns out every Jordan block, the characteristic and minimal polynomials are equal, and they are equal to x minus lambda to the mi. But now, suppose I have two different Jordan blocks with the same lambda, with the same eigenvalue. Okay, then why does this keep breaking? With the same eigenvalue, then it need not. So suppose one of them is size 3 by 3 and one of them is size 4 by 4. Then I would get x minus lambda cube and x minus lambda fourth. But notice that x minus lambda fourth kills both of the Jordan blocks already. One of them is killed by x minus lambda cube and therefore by x minus lambda fourth. The other is killed by x minus lambda fourth, meaning a minus lambda I to the fourth is 0. That kind of thing. Right? So I just need to take the largest power of lambda for every lambda that occurs. The largest size of the Jordan block for every lambda. And that's what it is. So I'll just say this. This is equal to, this is the product, lambda being an eigenvalue, x minus lambda to the max of what? Max of mi, such that lambda I equals lambda. Take the largest size for which lambda I equals lambda. Among them, the sizes are mi. Take the largest of the mi's. Look at x minus lambda raised to that power. And that's what the minimal polynomial is. So these are all corollaries, consequences, which I'm not going to prove. And in particular, yeah. So when are the characteristic and minimal polynomials equal? They're equal if and only if every eigenvalue occurs for a single Jordan block. So for example, for a single Jordan block itself, the characteristic and minimal polynomials are equal. In particular, P min of A equals PA of x, the characteristic polynomial, if and only if every eigenvalue occurs in at most one Jordan block. Oh, well, if it's an eigenvalue, then it has to occur in at least one. So every eigenvalue occurs in a unique double block. Okay, so these are all sort of standard facts. You are obviously free to use them, etc. etc. Okay, now let's go towards the proof. The proof is in several steps. As I said, it's taken from a Princeton University webpage, math department webpage. Okay, so towards the proof. The proof of Jordan's canonical form theorem. In several steps. Okay, let's start with the first step. I'll call it lemma 1. As I said, my goal today is to prove until lemma 3. There are 3 lemmas. The first one is very easy, so I'll just prove it. The first one is actually not even about something where transformation, all of those eigenvalues and so on. It's just a rank nullity transfer lemma. Okay, it's literally as simple as that. So say dim V. So no assumptions. Suppose I have a finite dimensional vector space over a field, and let's say T from V to V, of course, is linear, and that's it. No assumptions on T or V. Okay. If let's say the kernel of T. So remember that for every linear transformation, of course, we have a kernel T inverse of 0, and we have an image of T, the outputs of all vectors. Suppose this, I can move this dimension F. Suppose this is just a 0 vector. Right? Suppose that is just a 0 vector, then V is the direct sum of kernel elements. That is the theorem. That is the lemma. It's just a small step, but we will use it. Okay, so basically the idea is very simple. Let's call this W1. Let's call this W2. Since T is from V to V, so W1 and W2 are both subspaces of V. We know that the intersection is 0. And then what do we know about the dimension of the sum of these two? It is equal to the sum of the dimensions minus the dimension of the intersection. But the intersection is 0, so it's equal to the sum of the dimensions. Okay, I think that's the correct way to prove it. So I don't know why I didn't. Where is my pen? I just had it here. 1 second. Here we go. So. Okay. So the first thing is if you have two subspaces which intersect in 0, then their sum is direct. So proof. I'll just call W1 as this and W2 as this. So since W1 intersect W2 equals 0, their sum is direct. I'll literally say that. Let's write it down. And of course, this direct sum is a subspace of V. We want to prove it equals V. Why is it equal to? Okay, so let's calculate the dimension. Okay, the dimension of W. And dimension of W1 plus W2, the direct sum, which is the subspace of V. I want to claim it equals dimension of V. So first of all, as we said, it is dimension of W1 plus W2. And then this is the GCD LCM kind of lemma for vector spaces, which we proved a long time ago, and now we will actually use it. Is equal to dimension W1 minus dimension intersection. Okay, but what is W1? It is the kernel. What is W2? It is the image. What is the dimension of the image? It's called the rank. The dimension of the kernel is called the nullity. And we do have the rank nullity theorem, which says what it is. Right? So this is equal to nullity of T plus rank of T minus 0, because the intersection is given to be 0. Well, what is rank plus nullity? The rank nullity theorem tells us this is dimension of V. So here you have a vector space, W1 directs from W2, which is a subspace of V, and the dimensions agree. Therefore, W1 directs from W2 must be V. So that is the lemma. Okay, so it's not small by any means, the proof, but there's one trick, is you have to use the rank nullity theorem. So it's nice, right? That we are suddenly seeing all these. This is the point of mathematics in general, right? You use all these old results you have proved earlier, and now they're all ready to serve you when you want them to. Okay, great. So this is lemma 1. Now let's go to lemma 2. And as I said, I'll do lemma 2, lemma 3, and then I'm done for today. Next time we'll start with nilpotent maps and go on to lemma 4 and so on. Okay, lemma 2 has a bigger proof. That's fine. Okay, lemma 2. So what does lemma 2 say? Lemma 2 says, suppose I have again the usual finite dimensional vector space, but this time with a linear map, I'm extra imposing condition of the eigenvalue. So say again, give me as infinity. And then T, of course, is in lin dV. And T has an eigenvalue. Maybe I could say and has an eigenvalue lambda. Of course, obviously lambda is in the scalars. Okay, so now I'm going to define not the eigenspace, but the generalized eigenspace. Define the generalized lambda eigenspace. I will use the American spelling with a Z. I'll call this V prime lambda, not V lambda. V lambda is the actual eigenspace. This is the set of all vectors V in V, such that what would we ordinarily say? We would say that T minus lambda identity times V is 0. Now I will say there is some integer power, T minus lambda identity square of V is 0 or cube of V is 0. There is some integer power such that that gives V. So that for some m bigger equals 0, bigger equals 1, T minus lambda identity to the m of V equals 0. Okay, that is the thing. This is called generalized eigenspace. Okay. Then there are two parts to the theorem. One is that you see every vector in this eigenspace has some integer power of this transformation that gives it. But maybe I can keep finding bigger and bigger and bigger integer powers. Maybe the same one integer power doesn't work for everything. That's not the case. What the first statement is there exists an integer r such that this is equal to, there is an r bigger equals 1 such that v prime lambda is literally the kernel of t minus lambda identity to r. That is the first statement. The second statement is v is actually equal to the kernel of this plus the image of this in that sense. So clearly we are going to use lemma 1. This is just v1, v lambda, v prime lambda, sorry, direct sum the image. Okay. And third, both these spaces, or maybe I should say here itself, and both these spaces are t stable. I might skip this depending on the time situation. We'll see. Or I might not. Let's see. I think that was all. So let's prove this. And then the third lemma is not that, doesn't have a huge proof, so that should be fine. The third lemma is roughly this much of a proof. So. And then we will stop for today and then continue next week. Sorry, maybe I should have put that. If you want to use this, of course. I'll have to delete it. I'll have to erase it anyway, I think, but we'll see. Proof. Okay, so first of all, you want to say that this v prime lambda is a subspace. Right? I think that's what we want to say. So let's see. And that is obvious, right? Because if you have any vector in v prime lambda v, then any scalar multiple here would not change this exact condition. That is one. And suppose I have two vectors v1 and v2, so I get powers m1 and m2 that kill them. Well, then the bigger power kills both of them. And therefore the bigger power kills their sum. And so again v1 plus v2 is that set. So I don't even know. V comma m c times v comma m. I'll just say it this way and you figure out what this means. v1 comma m1, v2 comma m2. So v1 plus v2 is killed by the power which is the max of m1. That's power of the t minus lambda. If I leave it to you guys to decode what this means. Okay, but that's basically what it means. Okay, so that's the first step. So therefore now v prime lambda. And the second thing now is, okay, everything is finite dimensional. If this is finite dimensional, then this is being a subspace, now it has a finite basis. By A, so you see, we build one from here. A, v prime lambda has a finite basis. Should I take an ordered one? Do I want to take an ordered one? Apparently not. Say v1, v2, vk. Why not? With t minus lambda identity to the mi of vi equals 0 for all I. But then you see, if it's killed by mi, then it's killed by the max of the mi's, which is the same power for all of here. So let me just say set I equals max of mi. So that is the statement of the lemma. I claim that is the type. Okay, then clearly, since t minus lambda identity to the mi is 0, we multiply by some more powers, p minus lambda identity to the r is 0. Then t minus lambda I to the r kills all basis vectors vi. But this forms the basis of this b prime lambda. If it kills all the basis vectors, it kills all linear combinations, therefore it kills the stack. Hence kills b prime lambda. What does this mean? It means that b prime lambda is in the kernel of this thing. Because it is killed by the power. Okay? I claim the reverse equation is obvious. And it is obvious because of this. If you take any vector which is killed by this power, well then that vector, you put r here, that vector satisfies this condition, and so of course it's sitting inside here. This is by definition. And this one is by the previous statement. Therefore they are equal. That is what part 1 was. This proves part 1. I should have said part 1 here. So part 1 is up, right? Because that's what we want to say. Part 2 is slightly more interesting maybe. The first claim I claim is that if you look at the image set, okay, and intersect that with look at the image set, but the image of V, so the image on V, intersect that with V prime lambda, which is the kernel. The first claim is that the intersection is 0. That you want to use lemma 1, right? So you have to, in order to use lemma 1, you must say that the intersection is 0 and therefore we are none. So why is that true? So by lemma 1, it suffices to show what? It shows show that the intersection of these two spaces is 0. Image P minus lambda identity to the R intersect D prime lambda is simply the 0 vector. How do you show this? So suppose they have a vector. Okay? So indeed suppose, so proof. Right, because if I show this, then by lemma 1, whenever two spaces, the image and the kernel of linear transformation intersect at 0, the direct sum is equal to all of the space by the rank nullity theorem. Right? So let's prove this. So suppose to say U belongs to that thing, image of T minus lambda I identity to the R intersect D prime lambda. Then what can you know that? So first of all, U must be equal to, it's in the image, right? So that means it is equal to, that's what it is. Now did I say U here? Yeah. So that means what? So by the image part, U is equal to T minus lambda identity to the R applied to some vector V. Yes? So far so good. Because that's the point of being in the image. But now U is also in the kernel. So, but what was this? This was the kernel of these things. So, which means if you apply t minus lambda identity to the R to U, you get 0. And 0 equals t minus lambda identity to the R of U. But that is t minus lambda identity further. So, it's t minus lambda identity to the 2R applied to V. And so, look, here is a vector V. So, I should have said for some V in V. What is V here? For some V in V, and this happens. But you see, that means you have found a vector in the vector space V such that some power of t minus lambda kills that vector. This means that itself V itself must be in V prime lambda. And now by part A or part 1 or whatever we called it, we know that that is equal to kernel of t minus lambda and V. But you see, U was exactly that transformation applied to V. What do you get when you apply it to V? You get 0. And so that's it. We are done. We wanted to prove that any vector U belongs to this must equal 0, and we just did. Okay, good. So I think that was that. The final part was okay. Sorry. Moreover, why are both P as 0? Maybe I'll call this 2, so I'll call this 3. It remains to show that both the kernel and the image are stable under T. Well, okay, let's see why. So, okay, let's say, let's say U belongs to the image of t minus lambda identity to the R. That means U is equal to something like that. Let's just do this. I'll see if I can do this. If not, I will run away and we will continue. So U equals t minus lambda identity to the R times V for some. Let's look at TU. I want to prove TU is also in the image, right? So TU is U is lambda U plus t minus lambda identity times U. Yes? And t minus lambda identity times U is equal to. Okay, now the first thing you see, so U is indeed here. It's lambda t minus lambda identity. Yeah, so this is just the definition of U. Plus, maybe I should put this over here, plus t minus. Again, here it will be t minus lambda identity to the R times 1 extra power. So R plus 1 times V. And now you can check this is obviously in the image, right? This is exactly t minus, I can take this thing common, apply to the vector, there's only R, so this is lambda V plus t minus lambda identity times. Oh, I need not have done all this. Oh, jeez. Okay, this is horrible. I don't need to do all of this calculation. The point is t minus lambda identity commutes with t, and therefore we are done. Very sorry, since I didn't think it through. This is t times t minus lambda identity to the R times V. But t and these guys commute, because it's t commutes with the identity, t commutes with t, so it commutes with this. So which means this is just t minus lambda identity to the R t. And therefore it is indeed in the image. So that's fine. Check. Secondly, what about the kernel? Say similarly, belongs to the kernel. It's the same idea, right? So then that means that then let's look at t minus lambda. I want to show that t times v or t applied to v also has the same property. But that's again obvious because t commutes to these guys. So it's like this is like t of v obviously. But t commutes to these guys again. So this is t applied to t minus lambda identity to the r of v. That's just t applied to 0 and that is again 0. So indeed, those things are stable under t. That is just calculation. Great, so that's lemma 2 is finished. Now let me write down lemma 3, prove it, and we can stop. Well, maybe I'll define the important transformations or something, but let's see. Okay, so lemma 3. What is lemma 3? Again, the same thing. This time I assume a little more. So every lemma I assume, say dim v is less than infinity, v is finite dimension over f, t in lim vb, and the characteristic polynomial of t. Now this time we assume it splits as a product of a linear factor. It's a product of linear factors. Linear factors in Fx, of course. Okay? Okay, I think we have just passed 1.5 hours, so I'll stop. I won't define the important things right now. Okay, fine. Okay. And now, okay, now I need to write down distinct eigenvalues. So say lambda 1, lambda 2, lambda k are the distinct eigenvalues. Of t. Then, there exist integers such that basically t, the vector space is a direct sum of the kernels of these guys. There exists R1, R2, Rk, natural numbers such that, so meaning positive integers. Sorry, v equals kernel t minus lambda I identity to the Ri. I obviously goes from 1 to k. And that's, and each summand is with each summand there are t-stable subspace. Each summand a t-stable subspace. That is the theorem. That's the lemma. And basically, it follows from the previous lemma, just by induction, the image itself. So basically, this is like that simultaneous diagonalizability part, where we verified that the remaining part was also t-stable. Well, that is why here you see the kernel of t minus lambda to the r is t-stable, and the remaining part, which was the image, is also t-stable and of smaller dimension. So now I can play the same game with calling it this guy as my new v. So start with the old v, break it, so take lambda 1, break it into lambda t minus image plus this kernel. Now the kernel will keep it as it is, that is one of the factors here. The image is the remaining guy, it has smaller dimension and it is t-stable. That means the image now can play the role of this v. Therefore it has some other eigenvalue, lambda 2 through lambda k. And that's where you take out lambda 2 part again. And then the image of that inside the image of this will play the role of the v again. From there you take out the lambda 3 component and keep going. That's the proof. I'll just write it up and then we are done. Okay. So basically the proof is by induction on the dimension of v. So you see, we used lemma 1 to prove lemma 2, and now we will, did I say that? That was in part 1. By induction on n dimension of V. The base case is n equals 1, that is just obvious. Because in this case, the T itself gives you the eigenvalue. I won't even write anything more. You can just say R equals 1. K equals 1, R equals 1, and so on and so forth. Okay, fine. So the induction step is what we need to write down, and I'll just save there and we'll stop. So you see, I mean, we are still nowhere close to talking about Jordan canonical forms, except this is already actually almost there. These are exactly the kernel of this power Ri, where Ri is the maximum, the biggest size of the Jordan block. This is, the kernel of this is precisely those parts of it on which the transformation T acts by lambda I and a little more. And that little more is what is called a nilpotent operator, where T minus lambda is nilpotent operator, like the differentiation operator. The differentiation operator was nilpotent. And I should probably write this down as it's something. For next time, I will mention that del on Vn. So that's the whole point of showing it. Right? So basically, each of these kernels is going to be a part of the whole vector space on which the T operator acts in Jordan block fashion, with the biggest block of size Ri. So I can choose the smallest possible such Ri's and so on. Yeah, so I'll choose the smallest possible Ri's that work for this. Then that smallest possible Ri is the biggest possible block of the Jordan block with lambda I in the diagrams. There may be multiple such blocks. The biggest one has size I. And so that's it. We are actually getting there. We are getting towards the Jordan canonical form, even though I don't know, I haven't really said anything about the Jordan canonical form, or there exists some basis, some eigenbasis, or not. There exists some basis with respect to it. Something, nothing have I said. I haven't, in particular, I haven't told you about the basis yet. But this thing is basically going to say that the way the transformation acts on certain parts, certain subspaces, is exactly you through Jordan blocks with lambda I on the diagram. So we will get there. Okay, but let's quickly finish this and stop for today. It's past 11 p.m. now, and I have to still stay awake for at least 1.5 hours more. Too many other things to do, but fine. So let's finish this. Yes, so base case, induction step. So now n is of course bigger equals 2. We know that we are assuming the result holds for all smaller dimensional subspaces or vector spaces. Okay, so now literally take lambda 1. So no. So okay, first of all, given V, there is an eigenvalue. We assume that all the eigenvalues exist. So now given, so let lambda 1 be an eigenvalue of T on V. By lemma 2, we know this thing. Right? V equals kernel T minus lambda 1 identity to the R1 directs on the image. Let's call it V2. Let's call it V prime here. There, V prime equals the image is in the T state. T minus lambda 1 identity to the R1 is T stable and of smaller dimension. And that's the key. The remaining part is of smaller dimension and T stable. So I can use V prime instead and apply the induction hypothesis. Therefore, now I can say, look, the characteristic polynomial also divides that because it's a direct sum of t stable, because these are t stable subspaces. Therefore, if you take a basis, so basically what I'm saying is, so if I call this kernel as let's say V0, so T of V is sort of T V0 block diagonal matrix T V prime, which means that the characteristic polynomial of T also is equal to product of those two characteristic polynomials, and therefore each of those two also splits as a product of linear factors, because I know in fact what the TV0 is. On this thing TV0, the characteristic polynomial is exactly x minus lambda 1 to the. Hence, P characteristic polynomial on V prime of x is P T of x divided by x minus lambda 1 to the whatever, however many dimensions there are, R1. No, not R1. Dim of V0. Also splits over F. So this is probably slightly imprecise, like more work has to be done, but you can do this. And I can do this, but I'm too tired right now to do this. Splits over F. Which means now that yes, this is indeed a, so over Vz over V prime, dimension V prime is less than infinity, check. Does P go from V prime to V prime? Yes, because V prime is T stable. Check. Does the characteristic polynomial on V prime of T split into a product? Yes, sort of. I mean, it does, I'm just not saying. Now, what are the distinct eigenvalues? Will be exhausted all the eigenvalues for lambda 1. That's the whole point of the fact that this is finishing off all the lambda 1 eigenvalues. So the remaining distinct eigenvalues are lambda 2 through lambda k. Okay. And has distinct eigenvalues. Moreover, the dimension is strictly smaller than the dimension of V. So by the induction hypothesis, V prime is the kernel of the remaining part, the direct sum. And therefore V is the sum of the first one and the remaining part, and we are done. And that's the proof. Now, so I'll just say now we are, so fine. By induction hypothesis, V prime is the direct sum of the kernel T minus lambda I, the identity, to the Ri. I goes from 2 to k. So strictly speaking, I should say, and this is the slight subtlety, this is the kernel of T when T acts on V1, on V prime. And this is identity of V prime. So what is the guarantee? But here, these are all T acting on V. So last step is to show, therefore, so the last step is to show that this kernel, if you look at the kernel on kernel over V of T minus lambda 2 times identity or T minus lambda 3 times identity, these kernels actually sit inside V prime itself. Okay. And this again, I don't know if I want to do it right now, but yes. Let me just say the claim. Kernel of T minus lambda 2 identity. Let's just say lambda 2 because I can take lambda anything bigger than 1. R2 on V prime equals kernel on V itself, the T minus lambda 2 identity. In fact, so as I said, R2, or I can take lambda j for j bigger than 1. For all j bigger than 1. And therefore, now, therefore, I can remove the v prime here and just say that I'm done with these are all the kernel on v's. But now v prime is therefore a direct sum from 2 to k, and the v is this direct sum from 2 to k plus the sum for 1. And therefore, this implies this here. The claim implies. So it remains to prove the claim. And do I want to do it right now? No, I think we are already well past. I think, yeah, oh god, yes. We are well past the time, so let's not do it right now. So, okay, so we'll stop here. Yeah, I think it's like almost 1 hour 45 minutes or something. So, yeah, it's well past the time to stop. But yes, that claim can be proved, and therefore, I'm not probably going to prove it. Let's see. Depending on how much time I have next time. I could actually just do this much. We'll see. Fine. Okay, so that's it for today. We will continue next time with the proof of, we'll start with nilpotent operators and continue and finish the proof of the Jordan canonical form theorem. That's the goal for next time. And then we will see how much time we have and what to do. Okay, this is it for now.